Sorry if I sound frustrated. I've just been making a lot of little mistakes today, and as much as I'm prepared to give out this set of notes, I'm totally prepared to make a mistake and lose my mind as I go through this. This is the chain rule, where we have kind of this derivative of the inside times derivative of the outside idea. Derivative of the inside times derivative of the outside. You guys saw it when you were in parametrics, that I could kind of divide them to get to here, but that's not really exactly what we're looking at anymore. I have more complicated functions where, as much as this function is based on x and y, what if x and y were also based on t? This is totally what we're used to at this point in this class, but how do I take these derivatives? Can I find dz dt? What does it even mean when I find dz dt? So we have to be mindful of what the tree diagram looks like of this function, if it's possible to get this derivative of the outside times derivative of the inside concept. And also notice, we saw this a lot in that last lesson of linear approximation, the fact that these dx's will cancel. And what you'll end up seeing is that, hey, this results in the part of z that depends on t, it comes from x. This is the part of z that depends on t, that comes from y. And since z only depends on x and y, and therefore t, I'm able to find the total change in t by combining those changes from x and y. Let's look how this continues. Let's just do a little bit. Let's crunch some numbers here. First, let's build out the tree diagram. Z is dependent on x and y, right? Z over here is a function of x and y, but x depends on t. And y also depends on t. So I can look and see, hey, z is not solely reliant on x. Z is not solely reliant on y. And it's probably been a while that you've been wondering, hey, Mr. P, you keep switching between partials and regular. Even here, in the middle of this formula, you're switching between partials and normal differentials. Why? Well, I can't say that z is entirely dependent on x. It's only partially dependent on x. But you know what I can say? I can say that x is completely dependent on t. I can say that y is completely dependent on t. And I can draw that connection that z can be directly dependent on t. So if I can show that direct linear dependence, then I can write a full-blown differential. If I have this partial split where it's going in multiple directions, I have to show that partiality through the partial derivative. All right? So if I want to go find dz dt as this question suggests, I need to find the part of z that depends on x, and then the part of x that depends on t. Watch. That should be a partial. Right after that whole conversation, I freaking blow the first one. Partial z, partial x. I'm just going to do a chain, or just some partial derivative here. Now, when I go to take the derivative here, this is dx dt. Well, dx dt is just going to be 2 cosine 2t. How clean. If I do the same thing for y, partial of z that depends on y, well, that would be x squared plus 12xy cubed. And y's entire dependence on t can be written as such. Not only that, it does give me that t equals 0. So this gets really messy real quick. But when t is 0, my original functions are 0 and 1. Their derivatives also have those values at 2 and 0. That also means that these would then have values. So a lot of kind of cascading here where I need to be mindful that I'm going to be plugging in t is 0 here, but I can't plug in t0 there. What is x when t is 0? x is 0. What is y when t is 0? Well, y is 1. So I'll keep that in mind as I build out what is dz dt. Because dz dt is kind of a monster when I'm multiplying. I have to multiply the change in x's and multiply the change in y's. And I know these words are here. This means z is completely dependent on t. And in fact, if we wanted to be miserable, terrible people, I could have taken this sine 2t and plugged it in here and squared it. I could have taken cosine t, plugged it in here. Right? I could have done this substitution. So this function of z would only be based in t. And then just take this ugly chain product rule combination to get me to what dz dt is. Again, generally when I do this, I'm going to start it looking like this: 2xy plus 3y to the fourth, and then I'm going to multiply by 2 cos 2t. There it is. There's going to be a calculus professor somewhere that absolutely cringes at me combining x, y, and t for a moment. Again, in a perfect world, if I had a whole world of space, I would be plugging in this sine, this cosine, this sine, this cosine for all of these. In fact, I'll probably pause the video and put up a sticky note with the whole thing. X squared plus 12xy cubed times negative sine t. Pause. Right, does that really look better? Right, this is the true and technical answer. If you're in Canvas and looking for your answer, you're doing something like this, you might even be distributing, combining, simplifying a little bit as you go through here. But that is the concept, that I have a derivative of z that's completely dependent on t, and these are all my t values. Now, thankfully, here it said when t equals 0. And when I run that calculation when t equals 0, I just get 6. In the biggest, most shocking turn of events there. All right. So with this in mind, with the lack of space to write that, because we have so many great examples to do today, we have this concept where z is the completely dependent variable. Z can do nothing on its own without x and y being intermediate variables, and that leaves t as an independent variable. So as t changes, x and y here in this middle layer intermediate, and z is the final dependent output layer. What if z is this? And G and H, oh gosh. What if more variables appear because it's Calc 3 and more variables always appear? Well, we just make more, don't we? Okay, Z is dependent on X and Y, and X and Y are both dependent on S and T. So, let's ask this question. Is Z completely dependent on T? No. Is Z completely dependent on S? No. Z is actually always dependent on multiple sources. So I can never write just like Z prime. Because it's so nuanced. Like, at least not in the typical way that you're ready for. We'll talk about this when we get to the back and do some dy dx stuff. But for now, because there's such heavy dependence over here on multiple things, any change would be partial. Partial z that depends on x, partial z depends on y, partial z that depends on s or t. Where again, like if I just jumped into the next example, like the math will show itself through. And we had this at the very top. dz dt times, again, x is not only dependent on t, so it's, or sorry, dz dx times partial x partial t plus partial z partial y times partial y partial t. Right? All of these things are partially on the others. And again, I can't even say that the z is entirely dependent on t, because it's not. I would have both of these. All right. Let's plug these in. Yeah, let's plug these in. Where dz dx would just be the same thing. E to the x times sine y. But then this dx dt would be 2st. Again, some calculus professor is crying somewhere while we're getting the right answer. This is going to be e to the x cosine y times this dy dt, 2st. Oh wait, not 2st. dy dt is s squared. Glad I caught it before I lost my mind. And so that means when I kind of summarize these things and put them all together, we're going to do the unthinkable. We're going to plug in all the x's and y's for s's and t's. So this final conversation shows what the issue is. E to the power st squared times sine of s squared t times 2st plus e to the power st squared times cosine of s squared t times s squared. Even if I wanted to simplify it and make it look a little bit nicer, this is just terrible stuff. Final answer. And now we understand why it's a partial, because even as I look at the change that's due to t, s is all over the place. Even though it's a constant, that constant still has a great effect. And even though I'm holding it constant, it still has a great effect. It doesn't go straight to 0. And we would see the same thing on the other side. Let's pick up the pace just a little bit. This would be partial z partial x times partial x partial s plus partial z partial y times partial y partial s. Right, I just know that the x's will cancel, the y's will cancel, and I'll get the part of z that depends on s from x, the part of z that depends on s from y, which will give me the total z that depends on s. I'm sure you guys believe in me to do that intermediate middle step. I would urge you to do it yourself as I write out my final answer here for the sake of time. 2st e to the st squared cosine s squared t. How terrible. All right, and in this case, we have more names for more things. And guess what? It's still kind of the same. Where z is a dependent, x and y are intermediate, and in these cases s and t are independent variables. I'm not an English teacher. Okay, and so like you would see the same cases. Like I could translate these formulas down for us, but yeah, we would see that the part of z that depends on s is the part of z that depends on x times the part of x that depends on s plus the part of z that depends on y times the part of y that depends on s. And that way, the and partial y's cancel, leaving me with this. And you see the exact same thing, just swap out for t's, or look at the very example at the top of our page. Now we need to get to implicit, where we're going to kind of move a pretty healthy pace here. Because it all depends on this initial condition, where f of xy equals 0. So that means that I have some function, y equals f of x, and so that translates this thing to be x comma y. x comma f of x is equal to 0. Well, then I know if I took those derivatives that we're used to, I would get the part of f that depends on x times dx dx. Oh. And the part of f that depends on y times, you guessed it, dy dx. And we know for a fact that dx dx just eliminates to make 1. So now, if I want to solve this thing out for dy dx, if I want to find my dy dx slope, partial f partial y dy dx equals negative partial f partial x. Divide it out one final time, dy dx equals, I'm going to switch my notation just a little bit for the sake of being clear. Beautiful. So if I know that y is a function of x, I could kind of shorthand and get down here for dy dx. You guys already kind of saw this a little bit in parametrics, but the thing that always throws me off when I look at it is it's not just rise over run. It's kind of the other way around. Let's go back to AB and do this calculation. Find y prime, or dy dx, if this thing. So the first thing I have to do is move it over, because it said in the rules that it has to equal 0. All right, now we're going to go find those calculations. Big F of x is 3x squared minus 6y. Big F of y is 3y squared minus 6x. And now, I'm done. Free. Just like that. Negative f of x over f of y, f sub y. Even here, I can take it further. If I know this is true, which we're very used to doing at this point, where z is a function of x and y, this same concept holds true into the partials. But there is another trick up my sleeve here, where when I write out this big partial derivative, I know the dx dx is going to turn to 1. I guess that would be a partial z that partially depends on x. So here I know that dx dx equals 1. But in this case, this dy dx is actually just going to get, because we are in partial derivatives, y is constant. We're going to hold this situation where y is constant, so this becomes 0. And so now I have this df dx, or partial x partial f partial x partial f partial z times dz dx. Again, I keep saying d and I mean partials. So then I know that dz dx is negative f sub x over f sub z. And by the same exact token, if I wanted this, it'd be negative f sub y over f sub z. I would just change which one is. I'd be looking at dy, 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 and dx, dy would be 0 because it's held constant. So again, I'm looking at this example. Right, these look terrible. This looks massive, but I'm able to shortcut it. If I know that f of x, y, z is this x cubed plus y cubed plus z cubed plus 6xyz minus 1 equals 0, this shorthand now applies, where I can just jump to my answer. Partial z partial y is negative f sub y, 3y squared plus 6xz, over this thing partial z. Oops. And partial z partial x is the same exact concept. Negative f sub x over f sub z. I wrote it backwards, but I don't care. And there you go. That is the chain rule in 3D, and it feels nothing like the regular chain rule.